Hi guys, welcome to another Under the Hood of with me, Craig. Today we're going to be looking under the hood of GraphQL. In recent years, GraphQL has really taken off as a pattern, a library, a type system. It offers a lot which REST does not, and its standardization and flexibility has really helped in this adoption. When I began looking for a detailed explanation of how GraphQL works internally, I really struggled to find anything which was not too high level. I wanted to see how the schema, the query, the types, and resolvers all work together mechanically. It's not possible to focus on all parts in detail in this video, so I'll focus on the execution part of the query lifecycle. So this talk will be broken down into two parts. Part A is going to be an overview of GraphQL. We'll be looking at building the schema, the query lifecycle, the introspection system, and a couple of libraries. Part B is going to be building our own GraphQL executor, which includes some terminology. Step 1, which will be the schema and the query. Step 2 will be the execution itself. And then lastly, what have we missed? So we're going to start with an overview of GraphQL. First, we need to ask what is GraphQL, and there are a couple of answers. It's a type system. Type definitions define how data should look. They're written to show what is included and highlight the relationships, how things relate. This system definition language can be transformed into AST. It's also a formal language for querying data, what to fetch and from where, and it includes rules for validation, for execution against the query, using a query against the schema. That last point actually references the official specification, which defines the rules for types, validation, and executing the schema. It can be found at spec.graphql.org. There's also a documentation-friendly website at graphql.org/learn. All languages follow the spec, and the JS GraphQL library frequently references part of it, and we'll be looking at that library today as part of this section. So, building the schema. This is a very important part of a GraphQL application. As mentioned previously, it defines all of their types and their relationships together, and there are two steps to this. First step is passing the schema notation, which is usually found in some sort of schema.graphql file, into AST. The parser will throw errors if it's not a GraphQL schema. You can see the snippet from the types/schema.js file from the graphql-js codebase over there. And then step 2, where we transform the AST into objects and instances. We need a schema, which is a type instance of a GraphQL schema from the above snippet, GraphQL schema. We then need objects inside the schema which match types. For example, a scalar or an object. An example of a scalar is here. The native scalar types defined for GraphQL are ID, int, float, string, and boolean, but you can define your own inside your type system. So to summarize, essentially for building the schema, you turn this type with book, ID, title, and a list of authors into this JavaScript, where you've got these object instances being created, these class instances being created with fields. So almost all of the GraphQL types that you define will be object types. Object types have a name, but most importantly describe their fields. Here's a GraphQL schema. It looks like the below in the raw plain old JavaScript object form. And it holds AST information too, but the root query and types are found under the underscore type map property. Adding resolvers. So resolvers cannot be included in the GraphQL schema language, so they must be added separately. And they're actually added to the type map property under typemap.field.fields, underscore field, sorry, that's very important, .field. So after adding the resolvers, a schema object might look like below. So we've got this updated schema, we've got our type map query with our field users with the resolve, and then the type user with our field's address. And they both got resolve function, you can see. So from the HTTP request side, the community is largely standardized on a HTTP post method. But what happens when the server receives that request? The GraphQL query spec outlines what is known as the request lifecycle. This details what happens when a request reaches the server to produce that result. And there are 3 steps that occur once the lifecycle is triggered. We've got step 1, which is the parsing step. Here the server turns the query into AST, and this includes 2 parts. There's lexical analysis, which is where GraphQL's lexer identifies the pieces, which is the words and the tokens of the GraphQL query, and assigns meaning to each of them. Then we've got the syntactic analysis, which is where the GraphQL parser then checks whether the pieces conform to the language syntax. So this is the grammar rules. If both these pass, the server can then move on. In GraphQL.js, this is all found under the parse.js file and function, you can see there. And this query, there's a query homepage, and becomes the AST on the right. You can actually play with this yourself on astexplorer.net if you select the GraphQL as a type. Step 2, validating the query. This step ensures the request is executable against the provided schema, and it's found under the validate.js in the GraphQL-js library. While it's usually run just before execute, it can be useful to run in isolation. For example, by a client before sending the query to the server. The benefit is that the validator could flag if there's an invalid query before it's sent to the server, potentially saving a HTTP request. It works by checking each field on the query AST document against the corresponding type definition in the schema object. It will do argument type compatibility checks as well as coercion checks. And then step 3 is execute query. This is by far the most intensive and the step I often found the most confusing in its mechanism, and we're actually going to be digging deeper into that in part B of this talk. So let's look at the process involved from a high level. First, it identifies the operations, so query or a mutation. Several queries or mutations could be made at once, and then it resolves each mutation. For step 2, each query or mutation is run in isolation. GraphQL iterates over each field in the selection set. If it's a scalar type, it resolves the field, calling execute field, else it will recurse the selection sets until it resolves to the scalar. The way this works is that the engine calls all fields on the root level at once, waits for all of them to return, and this includes any promises. Then after reading the return type, it cascades down the tree, calling all subfield resolvers with data from the parent resolver. Then it repeats the cascade on those field return types. So simply speaking, it calls the top level query initially, and then the root resolver for each type. The mechanism called scalar coercion comes into play here. Any values returned by the resolver are converted based on their return type. That's in order to uphold the API contract. For example, a resolver returning a string of 123, but with a number type attached to it, would be returned under a number 123, so it would be converted into a number. This is all found under the execute.js file inside of GraphQL.js, and then lastly, the result is returned. And as I mentioned before, this is going to be covered in part B of this talk. So I thought it was worth mentioning the introspection system. This is a really cool mechanism used by the GraphQL API schema to allow clients to learn what types and operations are supported and in what format. The clients can query the __ schema root type field in the GraphQL API, which is always available on the root type of the query. Actually, any interactive GraphQL UIs rely on sending an introspection query request to the server, which builds documentation and auto-completion with it. As part of my research, I covered many different libraries, so I thought it was worth giving a quick overview of the main ones in the JavaScript ecosystem. We've got GraphQL.js, which is the reference implementation of the GraphQL spec for JavaScript. It's also full of useful tools for building GraphQL servers, clients, and other things. It's a GitHub organization with many mono repositories, and it can perform the entire query lifecycle, including parsing the schema notation. The schema requires library-specific GraphQL schema instances, and also in order to be an executable schema, it requires to resolve functions. A couple of useful functions here. We've got the build client schema, which takes output of an introspection query and builds the schema out of it. We've also got a build AST schema, which once you've passed the schema into AST, this then transforms into a GraphQL schema type. GraphQL tools. It's an abstraction on top of GraphQL.js, houses lots of functionality, including generating a fully spec compliant schema and stitching multiple schemas together. Some useful functions are make executable schema, which takes type definition and resolvers, returns a GraphQL.js GraphQL schema instance. There's load schema sync, which you can point this to your source to load a schema from, and it will return a proper GraphQL schema instance, and then add resolvers to schema, takes a GraphQL schema, the instance, and the resolvers, and then returns an updated GraphQL schema. Very popular, that one. Apollo Server is an abstraction on GraphQL.js as well, but it also uses the GraphQL tools library for building the GraphQL server. Introspection is disabled on production by default, but on non-production, it uses introspection to expose the /GraphQL playground endpoint. Then lastly, Apollo Server. It's not really a library, but I thought it was worth a mention. Plugs into Apollo server and provides stats and information on your GraphQL server in real time, such as monitoring operations, tracking errors, and my favorite, which is profiling resolvers. I've got a screenshot there where you can actually see how it looks as it's done some profiling of every resolver within an object. So, on to part B. Here we will be building our own GraphQL execute function that a parsed query and our schema can run against. It's going to ignore any validation. We'll be using the GraphQL instance types to create a schema, ignoring the schema parsing step. We will not be using any of the functions that GraphQL.js provides. However, we will be using the type instances that they provide to build our valid schema. And we're going to be looking at 3 different scenarios to examine the mechanisms in place. So before we go any further, here are some of the common terms that you might find. There's definitions, which is name for a top-level statement in the document. Most GraphQL types you define will be object types, and they will have name and describe fields. Then there's operations, which is the type of request, is it a query or a mutation? There's selections. They are definitions that appear at a single level of a query. For example, field references, fragment spreads, and inline fragment spreads. And you can see more of that in the spec to look up those terms. Then there's execution context, which is data that must be available at all points during the query's execution. This includes the schema of the type system currently executing and fragments defined in the query document. It is passed into the resolver as context, and it's commonly used to represent an authenticated user or request-specific cache. Step 1. This is going to be split into 2 steps: the query and the execute, the query and the schema, and then the execute. So let's start with the query and the schema. So step 1 is to gather our AST and schema instances using the GraphQL.js, so they're ready for processing. The right image shows the types which we'll be importing from the GraphQL.js library. You can see there are 2 scalars, there's a string and int, an object, and a schema type. And then the query will look like this. You can see the middle image there. It's close to how a normal GraphQL schema would run, except usually there's an extra parse step before execution, and you can see how that would normally look below. So let's move on to our 3 scenarios. Scenario 1 is a root query with resolver arguments. You can see the query there. Got the test with an argument, and that's it. We've got the hard-coded query AST on the right, and the schema on the left, where test is a string. You can see we're building the schema there on the left with the object instances. I would say that's more useful to look at than the AST. You can always look in the blog post below to reference the code again if you can't see anything. In the scenario 2, which is a root query with inner object and resolver arguments, you can see the query call again, we're calling test with an argument, and this time with an inner property. So again, the hard-coded AST is on the right, and the schema is on the left. You can see test is of type person, which has a name filled in. You can see that on the left person, then it's being added to our schema in the middle image. Finally, scenario 3. This is a different root type with inner object and resolver arguments. You can see the query where we're calling person with an inner property of name. Again, the hard-coded AST is on the right. You can always check the blog post linked if you do want to have a deeper look at any of this code. If you can't see anything here. And then there's the schema on the left. Person is now on the root query level, which is now on the same as tests. You can see that where we define person on the left and use it in the middle image. So, on to step 2, which is our execute. So now we have the setup complete for the 3 scenarios. We're going to look to build our actual execute function. The code is here, so let's walk through it. Starts on line 54. Here we call execute with our first definition as well as the types map. So we're limiting our proof of concept to the first operation, which we know is the query. In reality, it would iterate over the definitions. Inside the execute on line 3, we grab the query and the root types on line 6. Then we process the first selection in the selection set on line 8. Again, hard-coded for this proof of concept. We then grab the return type on line 10. This would be used for validation against the query result. I've omitted that part here. Line 11 creates an empty operations object to store any operation arguments on for later. On line 13, we check for arguments and grab the argument name and value. We could also grab the type on line 16, which would be used for validation. We define the execute field function on line 19, which we'll go through next. And then lastly, we call execute fields with our current selection set and an empty object. This empty object will make up our response to return. Now on to execute fields. It takes a selection set, a response object, and a field type as arguments. This is so it can call the query tree recursively and build the response data as we go along. Line 20, we iterate over the selection set selections, so this part does work with multiple selections. We grab the field on line 21 and check for it on the root query level on line 24. For scenario 1, the field is user, so it would check query._fields user.resolve, which does exist for scenario 1. So back to the code, if it does exist, which scenario 1 we know it does, we call the resolver with the argument name and the value, and then place the data returned from the resolver onto that field. For example, user. Place that onto the response in line 28. Line 32, we then check if the return types field exists on the schema's root types object. If so, we execute it with the parent's resolver data and then write that to the field on the response on line 36. For scenario 1, the return type is a string, which is a scalar, and as it's a scalar, this does not have the underscore fields property, so this would not trigger for scenario 1. However, for scenario 2, the return type is a person, which has got the underscore fields, one of which is name, but right now the field we're processing is test, so it wouldn't trigger until we recurse again. Line 40 and 41, we check if this selection has got selection sets itself, and if so, we execute those. We ham this selection set, the current response data for this field, and the current field name. So we're recursively calling execute functions, execute fields, with the deeper selection sets, and we're going to build up this single response to return. Scenario 2 will call the root query resolver first, then call execute fields again with the inner name field, where the field's resolver will be found and called with the existing resolver data. Lastly, we return the built response data on line 48. You can see user response. It's worth noting we've omitted any scalar checks here. With the real graphql-js.execute function, the field type is checked as part of the validation to make sure if it isn't a scalar that it has subselections. Although, when you look on line 32, the root.type return type.fields.field.resolve check is kind of a scalar check, although it's also checking for the resolve. So, now how do we check it works? In order to check it works, I wrote some unit tests that are found in the linked repository in the description. It includes some pure assertions as well as spies, and I initially ran all of them against the graphql-js function to ensure they were correctly written, so I made sure that they worked against the real one. I then swapped to using my executor. The schema objects are those that I showed earlier, but this is how it all fits together. I'm not going to walk through them all again, but here you can see scenario 1 on the left, scenario 2 on the right, scenario 3 on the left, and then on the right at the top is a summary of the data assertions. Below that is the test runner results, and you can see that it all works really nicely. I encourage anyone that's interested to check out the code that I've linked, play with the mechanism yourself, and just become familiar. So, as mentioned very early on, there are many additional parts to the real GraphQL-js executor, which we have omitted from our library. Some of those are the scalar type checks and scalar coercion, processing multiple queries and mutations at once, building a response data properly, not via parse by reference, handling some more complex scenarios, validating the query, which includes adding some errors, and then using the execution context, which would be passed to the resolvers. So that's it. Thanks so much for watching. I learned a huge amount from this GraphQL research, and I hope it was useful to you. You can find the repository for all this code here, and in the link in the description. Please check out my site for more under the hoods coming soon. Thanks.